So I gave my acknowledgement, so now let's continue with the lecture. So last week you saw a video from, I believe, last year, which basically covers the same material, but I don't know if everybody watched it, and it's always more difficult to watch it when it's taped rather than live. So I'll just go quickly through these slides, and then we will discuss some new ideas. So the general trend that I want to outline in this series of lectures is how quantum concepts in physics penetrate deeper and deeper into our various areas of science beyond physics. This whole story started at the turn of 19th and 20th centuries, and physics underwent a revolution. It's one of those scientific revolutions like Copernican revolution, then quantum revolution that changed the way we perceive the universe, not just physics and physical laws, but also deeper perception of reality, because quantum physics tells us that our senses are very illusory, and we don't always perceive the reality the way it is. But anyway, so quantum physics, I think, took about 40 to 50 years to develop, from empirical observations to a fundamental branch of science. And then gradually, these ideas entered into the next scale of nature, namely chemistry, how you can build chemical molecules from atoms, and chemical bonds are by and large based on quantum principles. And now, since about 2010 or so more than 10 years ago, we see a penetration of ideas stemming from quantum physics going into quantum biology, and that's the topic that we are here to discuss. It's not completely developed, but that's why it's even more interesting, because it's an emerging field, and it's actually, to me, it's very similar historically, comparing biology to physics. Physics is arguably, I'm a physicist, so I'm kind of proud to say, the most mature of all sciences, and has a history stretching back to 1600s, so about 400 years of systematic development, and very mathematical, which is the language of physics. Mathematics is the language of physics, but biology, of course, has been until recently more observational and sort of cataloging and classifying rather than mathematically describing. And now it's changing, and I think the reason for it is that we have both precise tools, experimental tools with which to observe cells and structures within cells, proteins, DNA. We know the structure of these players, elements that interact dynamically. And secondly, we can also use computational power. So modeling using quantitative means is very important, and more part and parcel of what we perceive as biological sciences or life sciences in general. Okay, so quantum biology, in my opinion, is a natural progression from quantitative biology, which is sounds similar but it's different, to quantum biology. And quantum biology means that we try to find initially examples of phenomena in living systems that cannot be explained other than by using quantum physics. And there is also a group of scientists who believe that there is actually a sort of different approach to it, namely, it's not quantum physics per se in biology, it's quantum physics in biology, but quantum-like biology. That means there are some principles at play which are not quite the same as in physics, but reminiscent of quantum principles. All right, and now, of course, everybody knows about quantum computing, which is a big topic. Every government in the West and beyond is investing money into quantum computing as the next frontier. So that leads us to the quantum brain. You know, if computers can do quantum computations, operations, why not our brain? And so I'll talk a little bit about this, not today perhaps, but next week. Why not indeed? I think there are some very powerful arguments in favor of this. And then that leads, of course, the brain, neuroscience, and the last frontier, consciousness. What is consciousness? Is it possibly a subtle quantum phenomenon that cannot be explained otherwise? A lot of people, especially in the artificial intelligence community, tend to believe that our thinking processes can be emulated or even improved by computers. I don't believe in that statement. I don't belong into this group of people because I think there's much more complex set of mechanisms at play than just sending electronic currents and performing binary operations. Perhaps with quantum computing, we can revisit this question. I'm not quite sure it's sufficient. And then I'll say a few things about the experiments which I'm actually involved in, linking, so from consciousness to no consciousness. There's a very neat dial that you can turn and turn off consciousness at will, more or less, not only for humans, but animals as well. And that's called anesthesia. And we have a large set of compounds which can do the trick. We've known it for more than a century and a half, and we still don't know how it works. But these experiments that I'm involved in right now test some of the hypotheses linking consciousness to quantum biology to anesthesiology. Because if we have a potential mechanism for consciousness, which is quantum, then we should be able to turn this mechanism off by the presence of anesthetic molecules. And so that will be something I'll talk about later on. And then if time permits, I'll talk a little bit about quantum psychology and quantum psychiatry, which in my opinion are these examples of not necessarily quantum, but quantum-like areas. I would say ripe for colonization by physicists if they have interest in them. I do. So we are going back historically to the turn of 19th century, and there were a group of scientists who believed the end of science was near, that everything was discovered and nothing more needs to be discovered. Physics was finished, the rest is engineering, just optimization and improvement. But they were incredibly wrong. And as you know, technology of the 20th century is largely built on the achievements of quantum physics that was discovered through several experiments at the turn of experiments took place at the turn of 19th and 20th centuries, the modeling, the theory development in 20th century. And these experiments paved the way for the development of quantum physics. Currently, and as you will see, I'll try to make an argument that a similar situation exists in biology, that we only have a few examples here and there, and therefore we can dismiss it. No, if you even a single example that cannot be explained by the current paradigm means that there is something that we need to discover. And this actually, I want to make a single comment about this because outside of physics, not too many people are familiar with the term, the scientific method. The scientific method is something that goes back to the 17th century, Francis Bacon and others who developed basically a protocol how to do science properly. And that means first you start with empirical observations, and then you try to build a model of reality based on these observations. Next step is to hypothesize about a prediction for a new experiment that would be consistent with these observations. But you try to find holes in your theory or in your hypothesis, not to prove that you are right. The objective of science is to prove that you're wrong. And even a single experiment, therefore, that is in contradiction with your hypothesis means that your hypothesis is wrong. You're not trying to stretch reality to fit into your model. And this is a very important point, which most of the journalists these days don't understand. Of course, they're not scientists, so why should they understand? But as scientists, we have an obligation to educate people that the scientific method is and there's no such thing as complete science. Science is never complete because we always approximate reality by our models. And that also applies to quantum physics. It's only a manifestation through our current paradigms of how we see reality, typically at this smaller scales, because yes, quantum physics was initially adopted to understand elementary particles, electrons, protons, neutrons, atoms, eventually chemical molecules, and so on. This is here a list of scientific revolutions of 20th century, which is not just quantum physics, but quantum mechanics was, I would say, the central block here. But that included special theory of relativity and general theory of relativity, which basically told us that there is no such thing as absolute time. Special theory of relativity tells us that there is no absolute time. We don't even know if time exists, by the way. In physics, time is a parameter, it's a construct. And then general theory of relativity told us that there is that space and time actually are not devoid of content. That is, they bend and are curved in the presence of massive objects. So the presence of mass curves space-time. So when we think about space and time, typically we think in Cartesian terms. That's really old Descartes, old stuff. But it's so powerful that it shapes our imagination. And yeah, it's natural to think about space as, X, Y, Z, but it's not that. All right, so then quantum mechanics, I'll say a few words in a minute, and quantum chemistry and quantum field theory is an extension of quantum mechanics to a much more abstract and also correct way, but I will not have time to discuss the differences between quantum field theory and quantum mechanics. Suffice it to say that in 19th century, in my sort of humble opinion, the greatest achievement in 19th century science, in addition to Darwinian theory of evolution, was electromagnetism of Maxwell. And because of Maxwell, we now have everything that you see around you. The lights, the microphone, the cell phones, the projectors, everything is based on electromagnetism. And that theory introduced the concept of a field, as opposed to solid objects, masses, particles that we can relate to, we can touch. We cannot touch a field, but fields affect particles, just like the field of gravity. We all are brutally aware of the field of gravity. Try jumping from the second floor. I don't recommend, by the way, but something is pulling you down to the earth, right? So that means this is the most easy to understand field. But there are other fields, electromagnetic fields. We are bathed in electromagnetic radiation, although we don't feel it, except for the light, of course, which is also a certain form. All right. And then, of course, the biological revolution in terms of genetics, molecular biology, structural biology, and now systems biology. So there are currently, in my opinion, two exciting developments in biology, which are both related to physics in some way. One is quantum biology, which I'm warming up to talk about. and the second is systems biology. That is biology not of individual proteins or DNA molecules, but the biology of systems of genes, systems of proteins, systems of metabolites. The organism as a system of systems. And that's a profound change in terms of how we see and think about living systems. So yeah, physics engineering operates in terms of systems. So interactions are more important than players themselves. It's also known as the concept of emergence. New properties emerge as a result of interactions, not just throwing more proteins into the sack or changing the structure. It has to be connected by interactions. So these are the names and the names of the fields and the names of the scientists who built these fields over the past 3-4 centuries. And I have, again, no time to comment on all of it, but I mentioned Maxwell, Newton, everybody knows about, and then Boltzmann. Boltzmann I will mention specifically because he was a tragic figure in physics, a visionary, and which is often the case with visionary people who end up really badly, as they are misunderstood and criticized and ostracized. And he came up with the concept of entropy, and entropy has incredible, in my opinion, applicability to biological systems, because life, one of the key characteristics of life, everything that is alive struggles against entropy. Entropy is disorder. So as we build living systems, even bacteria or viruses, we build them to construct a particular organization, and that means lowering the entropy. Physics always leads to entropy increase. Life, biology decreases entropy, creates structure, symmetry, beauty, and so on. Right? So Boltzmann came up with this, and he formulated the laws of statistical thermodynamics, including the second law of thermodynamics, which talks about the inevitable increase of entropy. And on this note, Erwin Schrödinger, who is one of the creators of quantum mechanics, he was actually obsessed with this topic, and he wrote a book which is still relevant and was written in 1943 or 44 during the Second World War, called What is Life? And he grappled with the idea of living systems lowering entropy, and how can this be done? Because physical systems, engineering systems, they all succumb to the second law of thermodynamics, and entropy is being produced. So this is a quick timeline for the quantum revolution, about 4 decades, which sort of the central timeline for it occurred around mid-1920s to late 1920s with these conferences, Solvay conferences in Brussels, at the hotel, whose name I'm just... Hotel Metropole, right. Which I visited, by the way. I spent a year in Brussels and didn't miss that opportunity to visit the hotel. And here you see the collection of these giants. Every single one, I think, in this photograph got a Nobel Prize. There may be one exception, but I'm not so sure. So these people came to these conferences, and they're called Solvay because Solvay was a chemical company that sponsored the conferences. And they agreed on the foundation of quantum mechanics. And so at that time, there were kind of 2 separate perceptions of reality. Namely, one was particles, objects such as ping pong balls and tennis balls colliding, bouncing off, and and the laws of motion were consistent with Newtonian mechanics. And then the other was waves. Everybody was aware of ocean waves, acoustic waves, sound waves, electromagnetic waves. So that's Maxwell again. But what quantum mechanics did was to fuse these 2 concepts together in a kind of paradoxical and hard to understand manner. That is, quantum particles, these electrons and protons, they have both wave-like and particle-like wife. I'm thinking about my wife, I guess. Particle-like properties, and depending on how you probe them. So depending on the experiment, and that's another important thing that I really want you to think about for a second, because what quantum mechanics uncovered for us, revealed about the reality, is that no matter what observation you perform about anything, you interfere with the object of observation. And that's one connection to psychology, by the way. You know, I thought about this quite a bit, because when you interrogate an electron, a single particle, right, you have to hit it with something. You cannot, even a single ray of light, a single photon will disturb that particle. So there is no such thing as a separation of the system and the environment, which is so pervasive in physical thinking. But in psychology too, I think if you want to learn about somebody's mental state, you have to ask questions. And these questions may be disturbing the person, or affecting the mood or whatever you do. I don't think there are neutral questions, well, maybe you can ask about the weather, but even that is not so neutral, right? It's very nice and sunny today. I'm already smiling. Okay, so these were the 2 or 6 experiments which kind of shook the foundations of physics at the time, and all of these experiments threw a monkey wrench into the so-called classical physics. They were not explainable using Newtonian physics or even Maxwellian electromagnetism, which is also classical. And they required the introduction of quantum principles. And so what are these quantum principles, very briefly? The first is that we have to find something better than the description of a physical object in terms of mass, position, and time. You put a dot on the blackboard or whiteboard and say this is mass m at point x, y, z at time t. We don't know that. This is not possible. Instead of that x, y, z, we have a cloud-like representation. It means that there is only a probability that this object is somewhere around x, y, z, and it may be spread out. Now, the spread of that object is, the larger the spread, the smaller the object. So that's why for larger objects like ourselves or these tables and chairs, the spread is minuscule. It's still there. If you really probe it with very precise tools, you will find that there is some uncertainty in the position of this table, but really so small that for us it makes no difference, right? Something smaller than the size of a single atom. Well, that's, we can't see it, so it doesn't exist. But that's just a matter of perception. Our senses, of course, are limited. So that's number one, the perception of reality in terms of what objects look like. And so we physicists introduced the concept of the wave function. So in fact, in the beginning, quantum mechanics was called wave mechanics, and then it was relabeled, so to speak. But the wave function is an abstract representation of an object, a state of an object, not mx, y, z, t. It's psi, let's call it a Greek letter psi for the wave function. That was introduced by Erwin Schrödinger, which I mentioned earlier. That's number one. And then observation itself and the state of the object is a matter of probabilities, not certainties. We have to move away from certain. It's a huge revolution in thinking. Going back to Simon de Laplace in 18th century, who said that if you give him, the coordinates of all atoms in the universe, I'll predict the evolution of the universe, which is a complete absurdity in view of quantum mechanics. You cannot predict the location even of a single electron, let alone the universe. So you see, that's a major change in thinking. Okay, so probabilities, and the name quantum, quantization, relates to being able to assign integer numbers to units. So if you say quanta of energy, it started with energy, that is energy levels of microscopic systems such as electrons and protons come in units of 1, 2, 3. And the units are, and now we have to come up with an equation. Units of energy were introduced by none other than Max Planck as the product of a constant, which is, we now call the Planck constant H, and frequency F. That was another revolutionary idea, that the energy of the wave is proportional to the frequency of the wave. I don't know if it's intuitively obvious. I would say not, but it turned out to be correct. And the Planck constant H, maybe I'll just race ahead a bit. Here is the Planck constant in a different application. This is the formula that Planck came up with, a 1918 Nobel Prize in Physics. It seems like a big price for a little formula, but this formula means a lot. It means that the two things, as I mentioned, that light or photons, as we say in physics, is quantized. Although it seems like it's a continuum of brightness coming to your eyes. This is a large number of individual microscopic quanta of light, so they're called photons. And again, I'm struggling to call it a particle. It's a quasi-particle. It's not really something that has a mass. Light doesn't have a mass, but it behaves like a particle. When it hits an electron, it can kick it off and give it momentum. So you normally don't think like that. So a lot of, I'm focusing on concepts, right? Not much on formulas or really statements of some very specific applications. But so quantization, the duality, so wave-particle duality, it's a technical term. That means that physical objects are both waves and particles. You cannot say this is a particle, this is a wave. It's both at this level of microscopic abstraction. And because of this, we can use X-rays and electron scattering for imaging. X-rays, of course, also therapeutic applications. Now, so let me just race ahead a little bit. I don't want to spend too much time on the formulas, but that's the famous formula that Max Planck used to explain something which was known at the time, namely black body radiation. All systems emit electromagnetic waves at finite temperatures, and you can analyze the distribution of the intensity of these electromagnetic waves depending on the temperature. And in order to explain it quantitatively, Planck introduced this quantization formula, which is here in red. And that was almost against his conviction, because it's so unnatural to say energy has to come in units, just like, let's say, money comes in units of 1 cent, 2 cents, in dollars, but you cannot have 1.5 cents physically. Of course, electronically now you can, but basically it's like quantization of money. Energy is like money, is quantized in units. And by the way, I'll just preempt something. In biology, when you think about it, how many of you, let's say, can tell me if energy is quantized in biology? Can you think of some form of energy quantization? In other words, are there any integer units of energy in biological systems that you know of? No? Sorry? Yes, but that's a very large unit. Yes, but you can have 0.5 calories. I'll give you an answer to that question, and then we'll come back to it. It's actually ATP. The molecules of ATP carry, let's say, a quantum of energy, of biological or biochemical energy, and you cannot have 1.5 molecules of ATP. You can have 1, 2, 3, 4, 5, right? So there is a connection, and it's a very profound connection, by the way. There is another connection. I want to spend a few minutes on this one. The photoelectric effect. Albert Einstein was a genius, and he contributed enormously to physics, and he got Nobel Prize for this thing, which is maybe not the biggest discovery, but well, he should have been given 3 Nobel Prizes, but maybe 1 is enough. So what's the photoelectric effect? And you're familiar with this because if you go to a washroom these days, you know, you put your hands, there are photoreceptors, photocells that detect a break in the light that is coming through, right? Or in maybe less elegant way in urinals, the water starts flowing, you know, and so on. This is based on the photoelectric effect. That means light strikes a metal surface and has enough energy to kick out electrons from the valence bands of these metallic surfaces, and these electrons are free in the space between electrodes, and then they will be attracted to the cathode, the positive, because electrons are negatively charged, so they will be attracted, and the current will start flowing, and that current then can be used for, you know, triggering a cascade of events, including the water flow and so on. So the photoelectric effect requires a sufficient energy of the light to trigger this ejection of the electron from the surface of a metal. And that was a direct confirmation of Planck's formula, H times F, because energy is proportional to frequency. If you have high enough frequency, that happens. If the frequency is not high, sufficiently high, this will not happen. And that was detected. In other words, there is a critical amount of energy required, and the wavelength of light. So red light has less energy than blue light, because blue light has high frequency. And for example, blue light would trigger this effect and red would not. Depends on the metal surface and so on. So why is this of relevance to biology? We'll talk about it in these lectures. Can you think of something that requires light energy to do something? There you go. Exactly. This is very similar because photosynthetic systems are able to capture the energy of light and transfer this energy into electronic motion. And these electrons are then collected and used to make glucose out of CO2, water. And that's it. So yes, Einstein's. So you see, we have individual effects which are at least reminiscent in biology to those early experiments in physics, which were quantum. And by the way, so photosynthesis is this one of the most robustly quantum manifestations in biological systems. So far, of course, plants, some amoeba, and what else? Bacteria also. Some bacteria use photosynthesis, photosynthetic bacteria, some amoeba, some others, I don't remember, but we'll come to it. So it's not widespread, but it's important because what's important in biology? Metabolism, right? Energy transduction. Life means, to me at least, that you have to be able to convert energy into useful form. So metabolism, transformation of energy, is necessary, not sufficient, right? Because it's not sufficient. You have to have it, but it's not sufficient for living systems. Okay. So the photoelectric effect was an example of this wave-particle duality, because a wave, a photon, a wave of light, was able to act as if it was a particle by ejecting an electron, which we think of as a little ball that sits there, and, you know, it was kicked out and then attracted to the cathode and moved. Okay, and this the Heisenberg uncertainty principle is one of those weird things about quantum mechanics. We already heard about a few weird things like this wave-particle duality, like the wave function instead of the position coordinates. But this is probably one of the most difficult to understand, and it was formulated by Werner Heisenberg, a German physicist who stated the following, and there are some generalizations, that in quantum mechanics, you can there are inherently unknowable things about systems that you describe, and inherently impossible to know is for any object, quantum object, its position and its momentum. That means velocity at the same time. You can precisely pinpoint the object, but you will not know how fast it's moving. Or you can determine its velocity, but you cannot say where it is. You can only say that it's moving with 100 miles an hour, but I don't know where it is. So that's inherent, and therefore it gives us the limits of our knowledge, even for single particles. And again, back to Simon de Laplace, who didn't know about this, of course. It's actually not even related directly to the process of observation, just to the nature of quantum systems, and has to do with things without going into the sort of deep mathematical details, I cannot really say too much, except that it has to do with the mathematical foundations of quantum mechanics, which, by the way, were laid a century earlier in mathematics. Fortunately for us, because these physicists were very well trained in mathematics and knew, and the functional analysis is the field of mathematics that was used and uses permission operators. So operators were adopted by quantum physicists to describe what we call observables, such as velocity, position, energy. All of this was translated into the language of mathematics as these operators. And these operators, again, maybe I'll just say it and then we'll think about it for a second. These operators do not commute. What does it mean? That if you, let's say, measure position and then momentum or velocity first, and then do the opposite, velocity and then position, you get different results. The order of operations matters in quantum physics, not in classical physics. Classical physics doesn't matter which order you measure something. You measure the angular momentum or the velocity or the angle or the frequency. It doesn't matter. In quantum mechanics, it totally matters. And I think for this reason, that's another example where I think psychology could benefit from it, because the order of operations on, let's say, as a subject, maybe even in medicine, depending on which order you perform some procedures, you'll have different outcomes, right? It's not exchangeable. In quantum mechanics, it's definitely so, and there's no two ways about it. And okay, so structure of the atom was explained by Niels Bohr. The atomic model of Niels Bohr is somewhat similar to the solar system, where you have the nucleus, just like the sun, at the center, and then you have the planets, i.e. electrons, orbiting. But in principle, you could have planets orbiting in different positions, right? You can have different types of solar systems with different, but in terms of the quantum physics, atoms, orbits are quantized as well. It really cannot be 1.5 orbits. It has to be this, and we call them by quantum numbers. If you took chemistry, I'm sure you're familiar with the numbers n equals 1, so that, and 2, 3, 4, 5, and then you have orbital angular momentum, L, which are represented by letters S, P, D, F. They correspond to angular momentum 0, 1, 2, 3, and so on. So this is an example of implementation of quantum physics principles to explain atomic structures. And it's only one little stretch to go from atomic physics to chemistry, right? Because the chemistry is building molecules from atoms. And you get molecular orbitals instead of atomic orbitals, molecular orbitals, which are basically electronic clouds. Right? not electrons as ping pong balls anymore, but as density of charge density in a specific symmetric distribution. Okay, and that again, we are beneficiaries of all of this, not knowing about it most of the time. For example, spectroscopy, atomic molecular spectroscopy, is allowing us to not only see and determine the composition of distant stars, what they're composed of, because the spectra tell us about the transition between these electronic levels, but also about, let's say, the composition of tiny amounts of toxins in some substance. So in medicine, toxicology, you can use spectroscopy to analyze the composition. You can analyze the in pharmacology, the purity of substances by spectroscopic methods. If you want to have 99.9% pure drug for some disease, you can analyze the impurities by spectroscopic methods. So that's incredibly pollutants, car exhaust. You can monitor the atmosphere. We know what's happening in the atmosphere, not just by sending us a probe and bringing a sample. You don't have to do it. Spectroscopy will tell us about the composition of the atmosphere. Okay, let me just. Okay, so these postulates, 1927, the Solvay conference. These Nobel Prize winners assembled, and they came up with it's almost like I don't want to say it's a religious group, but I think the principles of the Roman Catholic religion or something like that. They formulated the principles of quantum mechanics, so they have to all agree on what's acceptable, and these were called the postulates of quantum mechanics. Maybe not principles. So postulate is softer, right? We postulate that this is, and the first one I told you about is the microscopic objects are characterized by a wave function. So it has to have some special properties. It's a integrable function, has to be well behaved and so on mathematically. And so that's Erwin Schrödinger with the wave function psi, which is allowed to give us partial information about the system in terms of the probability. The square of this function actually was interpreted as the probability distribution of where the object is. And all of you are familiar with maps, for example, maps that provide a distribution of before elections, right? Tendencies to vote Democratic, whether we have Liberal Party or Conservative here, or in the US, Democratic versus Republican, and you have red and blue, right? So it's a bit like that. It's not 100%, but you know that this is an orange state, which is kind of mixed. They are both leaning kind of in the middle between Republican and Democratic. So that will be a wave function for the at the macroscopic level, a probability distribution of voter preferences, right, or some other issues. So in physics, we would have the probability distribution of where the electron is. So these are the properties. All right, fine, and that's the probability distribution. The square of the function gives you the probability per volume. And that's the third one is the hardest. It's completely mathematical, and that's seemingly a break with 300-year tradition in physics. You know how to define mass. You know how to define velocity, measure the velocity. You know how to define momentum. Momentum in classical physics is mass times velocity, right? You know how to define angular momentum and things, torque, force, all of these things have been entrenched and defined by sort of operational instructions, how to measure the force, force of gravity, you extend the spring. Now this is really heavy duty. So they came up with this, that instead of these simple, easy to understand operations, we'll introduce mathematical objects. And they're called operators, Hermitian operators. Hermitian after the French mathematician Hermite. So, okay, so it should be Hermitian, but anyways. So momentum is, for example, the x component of momentum. In classical physics will be mass times v sub x component velocity. In quantum mechanics, it's here in the middle. It's actually partial derivative with respect to x. So it's a derivative. It's an operator, differential operator, multiplied by the Planck constant divided by 2 pi I square root of -1. I think I hazard a guess that no matter how long I would think about it, I would never come up with something like this out of the blue, right? I mean, it's really far from intuitive. But amazingly, can you still hear me? Because it shows that I'm disconnected from UWS. Or maybe not. But maybe you do. I can't advance now. Right? Yeah. Oh, yeah, I can. All right. So, well, amazingly, and again, that's a separate lecture for an hour to show how it fits with Newtonian physics. Was formulated very elegantly by Hamilton in terms of Hamiltonian mechanics, and there's a complete analogy between Hamiltonian mechanics, except for the commutators, these operators introduced by Hamilton commute, but in quantum mechanics they don't. But everything else looks exactly the same way. So it took a couple decades to find out that these definitions here, which are so abstract and so counterintuitive, make absolute perfect sense. But the last one is a beaut. Instead of Newton, so what do you do to replace Newton's equation of motion, right? For example, force equals mass times acceleration, right? Which we use to build machines and houses and all this. Well, so Erwin Schrödinger spent 2 weeks in the Alps on vacation in 1926, I think. Yes. And in between skiing, he was deriving all kinds of equations that would make sense. And he actually postulated this fourth equation, which is now the famous Schrödinger equation, that basically is replacing Newton's equations of motion for classical mechanics and quantum mechanics. That's the one. And the solution to this equation, let's say psi of xt is the evolution. So that means time dependence of the wave function. So if you want to know what this electron, let's say put an electron in a metal. A metal has a potential, and you give it a kick, maybe electric field applied to the ends of this metal. You want to predict how this electron will behave. And that's the basis of electronics, by the way, semiconductors, everything like that. You solve this equation, and it tells you, not again precisely, but it gives you the probability of this electrons moving at a particular speed to the left, to the right, how the wave function distributes itself, and so on. So I hope I'm sort of conveying to you the differences and similarities between classical and quantum mechanics. But these are the most important things to keep in mind. Now, of course, let me just race forward. Things took about, I don't know, half a century to apply to more complex situations, from atoms to molecules. From molecules, you start building solids, right? So semiconductors, metals, superconductors, And for every application like this, superfluids, you get Nobel Prize. As simple as that, because these are important things to understand how superconducting devices work, squid, and so on, how lasers work, right? Lasers, another Nobel Prize for the discovery of lasers. Lasers are important because they are operating on the quantum principle of so light amplification, focused, single frequency, coherent wave, electromagnetic wave, as opposed to white light, which is a spectrum of frequencies. You have all colors mixed together, right? But lasers give you a single color, and that for this you need quantum mechanics. Now you can think about similar things in metaphorically in biological systems. For example, even a simple bacterium or a single cell organism like some protozoa, how do they orchestrate their movement? And it's they don't fall apart, and they move in unison. All the parts, all the proteins and the membranes are coordinated. So synchronization, orchestration, these kinds of things are hard to explain at the level of biological systems, unless there is some sort of, I'll use the term entanglement. They're coupled and therefore behave in synchrony. So this synchronization, we know from physics, can be done. And this is done by creating a collective wave function for, let's say, all the electrons in a metal. They form, we call it a Fermi sea. Fermi was an Italian physicist who solved some of these problems, got Nobel Prize, of course. And so we have examples of how to do this. And here is a slide showing the complexities of this, solving the Schrödinger equation for so-called many particle systems. Many particle systems are such as a piece of solid, could be a semiconductor, could be a crystal. How many particles are there? Astronomical numbers. How do you solve this? Well, you have to make approximation, but you can solve it. And so it's we talk about systems with particles on the order of Avogadro number, right? Avogadro number is 6 times 10 to the 23rd. That's a mole, right? A mole of something. And at that point, when you have 6 times 10 to the 23rd, just 10 to the 23rd, let's say, 1 and 23 zeros of particles, right? It's a humongous number of particles. How do you understand the system? So you have to make some take some shortcuts, make some approximations, but you can still solve it and predict the behavior of such a system. But the important thing is to understand interactions. And the human body is composed of, by the way, do you know how many cells are in the human body? Any rough idea? Anybody? Okay, 3.7 times 10 to the power 13. So 3.7 times 10 with 13 zeros. That's the brain. The human brain has 100 billion neurons only, and 10 times as many glia. So we're talking about cells, huge number of cells and different types, right? The human body has something like 200 types of cells, maybe more, but at least a few hundred. So this is where we need new concepts, I think, because the complexity is not in the just numbers, but diversity. So physics is paving the way for it because it deals with systems of many particles. And by the way, each cell, of course, will have, millions of proteins and phospholipids and sugars and all that. But we still have problems, translating physical ideas directly into biology. So one more thing, and then we have 20 minutes still, I think. We're getting close to biology, but I'm sort of throwing in biological concepts once in a while. one more thing that quantum mechanics introduced completely out of the blue is the concept of spin. So electrons and protons and neutrons, they all have a property which is called spin. And you can think about it as a spinning thing, right? Spinning around its own axis, like the Earth spins around its own axis, right? And makes a 24-hour full revolution around the axis. And of course, the Earth is spinning around the sun, and it's 365 days. So you can think about this, about electrons in each atom having orbital angular momentum and spinning around its own axis. However, this spinning around its own axis is metaphorical, because every electron has it, whether it's in an atom or outside of the atom, has the spin value, which leads to a so-called magnetic moment. And all of you are familiar with magnets, fridge magnets, for example, right? So magnetism has been known to humanity for thousands of years. Ancient Greeks and ancient Egyptians and in India, people knew about magnets, their properties. But magnetism is a quantum phenomenon. Can you believe this? That there's no magnetism without spin. Spin is the property that endows ferromagnets with the property, with the magnetic behavior, the compass needle, and so on. So, but the bottom line is the concept from quantum mechanics, spin, is necessary to explain magnetism. That's one example of the classically known or phenomenon, which is really quantum. And few people actually ponder about it and think about it. But coming now to biology, several objections to quantum biology. And you will hear, if you read papers, people criticizing quantum biology would say, number one, that biological systems, human beings, live at high temperatures. You might question that in Edmonton, but but by physical standards, even these are very high temperatures, right? Even minus 50 Celsius, because quantum physics is based on subtle interactions, which are disturbed by thermal vibrations. So thermal energies, and we'll come to it actually in a minute, probably, I hope. Thermal energy KT, so Boltzmann constant times the absolute temperature T, is free. So if you're in this room, we are 20, let's say 1 Celsius. So it's 294 degrees Kelvin, or 5, multiplied by the Boltzmann constant. That energy is bombarding you all the time, because the air molecules, are at this temperature, and they hit, our surface and transfer this energy to us. Our bodies are at 36.6 Celsius. So this energy is maintained at a constant level, and it's for free. So that's high energy in terms of is needed for enzymatic reactions to occur, for a lot of processes in biochemistry requiring that, otherwise it wouldn't occur. But from the physics point of view, it's causing problems. And the problem in technical terms is thermal decoherence. What does it mean? It means that if you are looking at this electron, we still don't know exactly where it is, but we know the wave function. When you add on top of it thermal energy, it all becomes fuzzy. And it's like, noise or the I don't know if you can relate to this, old-fashioned TV sets, and on the screen you see white and black, patterns, noisy pattern. You couldn't figure out what was going on sometimes. Interference. So that's basically what you would imagine. Instead of a nice picture of somebody or even a wave going through it, you suddenly see these blinking white and black and gray dots, pixels. Okay, so that's one objection, thermal energy. And so 37 or 36.6 Celsius is high energy, therefore a lot of noise. but magnets don't bother with, thermal noise doesn't destroy magnetism. Much higher, you have magnets at room temperature. So there are arguments that biological systems know how to overcome thermal noise, and they can still maintain quantum interactions. I will maybe skip this because this is again a little bit technical. But if you read about biological systems, one important phenomenon, and this is due to this famous Indian physicist Bose. This is an interesting story, by the way. He came up with this phenomenon of Bose condensation. We now call it Bose-Einstein condensation. So what is it? Under a certain set of conditions, quantum systems of many quantum particles can start behaving identically. That is, that's coherence. They all fall into the ground state and form like a army moving in lockstep. Instead of everybody, a crowd in front of a hockey arena or after the hockey game, everybody moving randomly. Now you have a well-organized army moving in the same direction. This is kind of Bose condensation, and quantum systems undergo it spontaneously under certain conditions. That would be nice because that could actually explain some of the coordination of activities in the biological system, Bose condensation. So this is an interesting anecdote because Bose tried to publish his groundbreaking paper and got rejected. Only when he wrote to Einstein, then of course it got published, and he became a fellow Royal Society without a PhD. So anyway, I don't want to sort of spoil this festive atmosphere with stories of colonialism, but this is an example of colonialism at its worst, or best, depending how you look at it. Okay, so Bose-Einstein condensation, and so just in passing, in quantum physics, there are two types of particles in general. When you look at their ensembles, so all particles can be divided into groups, either fermions or bosons. After Bose, bosons, fermions from Fermi, and fermions have this property that they do not like anybody else. They have to be by themselves in a given quantum state on the 1 or 0. So it's a binary system. And by the way, electrons are fermions. So that's why we can build the Mendeleev table of elements. That explains it. When you have fermions, you can only have 1 electron in a given state. And spin 1/2 allows the electrons to be in the same orbital, two electrons in the same orbital, right? Like 1s will have 2 electrons, 1 spin up, 1 spin down. And fermions and Fermi, it's called Fermi-Dirac statistics, explains things like conductivity of metals, semiconductors, and all of that. So it's necessary to understand the electronics through this. And the other is bosons, Bose-Einstein, and photons. So light is an example of a boson. That means that you can have as many particles in the same state as you want. So they're very collective, very friendly to everybody, come and join us. But fermions are not, they are antisocial. So that is important from another point of view, because we're now talking about statistics in physics, statistics in physics. Since we talked about systems of many particles, the way to understand systems of many particles is to use statistics, just like to understand society, you use statistics, right? Take opinion polls, you understand the public mood, are we for or against this, this proposition or whatever it is. The same with physical systems and I guess biological. And this is an important point that very few people actually understand about quantum biology. So quantum physics for most means a single particle hitting another particle, a collision between protons or neutrons or stuff like that, right? And then we see this, wave functions, but it's much more to quantum physics than that. And when you enter into the systems of many particles, such as crystals or magnets or superconductors, you're dealing with humongous numbers of particles. And still you can see quantum phenomena, not for a single particle, but for a huge number of particles. They manifest their quantum nature. That's the lesson for biology, because biology is exclusively about systems of many particles. So we should be able to see manifestations of quantum biological behavior in a statistical way, not in a single particle approximation. So why is that important? Okay, here, macroscopic quantum effects. The first objection to quantum biology is temperature. The second objection is that it's biology by definition means lots of particles, even a single bacterium. I don't remember how many atoms there are in a single bacterium, but it'll be billions of atoms at least, if not trillions. So it's not a single electron hitting a proton or something like that. It's lots of them. And here are examples of macroscopic, that means large scale quantum effects. Superconductivity is a quantum physics phenomenon par excellence. That means conductivity without resistance. And that occurs by electrons forming pairs called Cooper pairs and interacting via phonons, so lattice vibrations, and staying together as a pair. Superfluidity, lack of viscosity, superfluids, and then lasers. We talked about lasers, emission of photons with the same frequency in phase, so coherence. And then we have, okay, this is important, crystal vibrations, phonons. And this is one example where Einstein actually made a mistake. Einstein tried to explain specific heat of solids. And that means by how much the temperature of a solid changes if you add 1 calorie of heat. And it almost worked, but not quite, because at low temperature, as you lower the temperature of the solid, then the specific heat of the solid depends on the third power of temperature. And Einstein's model was exponential drop. So it was an exponential function of temperature. And the reason that he failed is that he assumed that every atom in a solid is out for itself, vibrating separately, independently, which actually is true of gases. So Einstein's theory of specific heat of solids applies to gases, but not to solids. Big mistake. So Peter Debye actually explained it. And the explanation is important because we will come back to it on Tuesday. Namely, looking at a solid from the quantum point of view, it's not that every atom vibrates independently. You have waves. These waves traverse the crystal, and they have to be in the boundary conditions because there is physical limitations. And also every atom or molecule forming the solid must be the node for this wave. The wave cannot have a node in between atoms. It has to be on every atom. Anyway, that's once you take this into account, you obtain the quantization of waves. The wavelengths are not arbitrary again. Just like if you look at the wavelengths in the ocean, you could think that every wavelength, that means, is it 1 meter, 2 meters, 2.5, is okay. No, in a solid, it has to be integer multiple of the distance between two atoms. Half the wavelength, actually. Half the wavelength has to be equal to the distance between two neighboring atoms. And that's natural quantization. And then you get the correct answer and all of that. So what's important about this? That you can see quantum principles through something that you measure macroscopically. You measure the specific heat of a piece of crystal, which is, let's say, 1 centimeter by 1 centimeter by 1 centimeter. You don't have to go into a single electron to see that this is quantized. Okay, and I think I'll give you an example of this thing in biology, that there is quantization at work and has to do with metabolism. We already kind of hinted at this. ATP is quantized, and there must be manifestations of quantization of energy production through something, and it is actually through metabolic rates. We'll discuss it next time. Okay. I will finish this with this list of some weird and some not so weird properties of quantum systems, which would be nice and are nice to, at least metaphorically, involve in understanding biological systems. We do not understand biological systems completely, for sure, but even at the level of sort of microscopic integration of the cardiovascular system, the pulmonary system, the nervous system, the immune system, how all of this synchronizes itself, you know, for the whole body to respond to stimuli, you know. All right, so this is the list. Stability of electrons and atoms. It means without quantum physics, you wouldn't have an atom, because an electron would fall on the nucleus by electrostatic attraction. Classes, you know, from first year physics, right? Opposite charges attract. Why is an electron not attracted to fall on the nucleus? Because nucleus is positive charge. You have to use quantization principle to obtain that. All right, that's kind of obvious. Now, the next one, complexity of symmetry. Now, the wave functions are these clouds that allow very complex arrangements in you know, large structures made of individual particles. But next ones are quite intriguing. Entanglement. Okay, what's entanglement? Entanglement means that two or more quantum systems can be coupled and maintain this entanglement even over macroscopic distances, or large distances. And I think that could be, I'll just give you one example. So you can construct a setup where you have one electron with spin up, the other with spin down, and allow them to move away from each other, fly away into the opposite directions in the space. And you then determine this orientation of the spin of one particle, and the other will have to have the opposite. So it manifests its state, even though it could be millions of miles away. So that's entanglement. They are always in this coupled state, if you will. Now, is there something like this in psychology, perhaps? I don't know if you had any experience with and being entangled with some other person, although you may not be talking to somebody or seeing somebody, you almost feel like you are connected over this space and time, right? So that coherence, laser. So coherence, again, that's the response in an integrated fashion to stimuli for the entire system. And then we'll talk a little bit about quantum information. Quantum information and quantum computing would be incredibly attractive ideas for the functioning of the brain. And in the last lecture, I'll talk about some of the mysteries of the brain and why we really have no clue why the brain is so powerful and it's actually powered by so little energy. So quantum interactions allow subtle amounts, tiny amounts of energy to do a lot. Yeah, we talked about quantum statistics. That would be like microscopic manifestations of quantum behavior in large systems. And tunneling, well, tunneling is known to occur in biochemistry, some reactions. So tunneling means that, classically speaking, a process is forbidden because a particle doesn't have enough energy to overcome a potential barrier. For example, thinking about throwing a tennis ball over a fence, and you don't have enough strength to throw it over the fence, so you throw it into the fence. A classical tennis ball would either drop down on the ground or be reflected back to you. A quantum tennis ball will have a probability to penetrate and almost like a ghost go through the fence. So this is for real, and that's happening in semiconductor systems where you have potential barriers and electrons tunnel through barriers which have energies higher than their own energy. So see, okay, these are the exotic, crazy, strange things that quantum systems allow you to do, and perhaps more than we think in the case of the human body. I think I'm done for today, and it's actually a good point because I talked about this already, and we'll talk about how all of this scales up. So at small scales we understand quite a bit. There is a fuzzy region which we're now probing as proteins. Is protein a quantum particle, or is it too big? Protein assemblies, cells, and so on. Thank you, and see you next Tuesday, if you still want me to.
Thank you.
Yeah.
Let me ask a question. You've been asked to write a book on quantum medicine. Are there other books by that title, or will this be the first?
Not to my knowledge, but of course, you never know. There may be something. It's
well, I think that's really exciting, and I modestly feel we had something to do with that, because the fact that you teach in a course that has the word medicine in it gave somebody an idea.
We want to be at the bleeding edge, and I think medicine. If we talk about quantum biology and biology. Again, historically, we have, let's say, I'll list and explain these 6 examples, 5 or 6 examples where quantum phenomena play a role in biology, but important ones: metabolism, energy transduction. This is key. If these things play a role in biology, and if metabolism is, maybe you will agree or not, metabolism is one of the most important pathological causes of diseases. If it goes wrong, you have a lot of problems, including Alzheimer's, cancer, cardiovascular, metabolic diabetes. Therefore, it's not a big stretch to say that there is importance of quantum phenomena for medicine and for health and well-being. Right? Mm-hmm. So there will be some, maybe at the end, I'll say a few things about how I see this, where quantum medicine can be applied and understood.
Yeah, but it's exciting to learn about a subject from the person who wrote the book on the subject. Well, now you will be that person. So, yeah.
And I hope you will help me write that book. Well, I already wrote actually 2/3 of it, so there's 1/3 to be done, cool. And it'll be published next year.
Yeah, excellent. Wow. Very cool. Okay, so the technology part of this will improve in the future. I had to spend a lot of time stringing cables that they ended up not using and so on. And we'll get it right. I think it's simplified by the fact that the people connecting by Zoom are not, as far as I know, asking questions. So,
but I have to say one thing. Being in the presence of living, thinking, intelligent individuals makes a big difference. Really, it is this entanglement. I feel completely entangled with you guys.
Yeah, and I mean, your lectures of all the lectures in the course have attracted the most people watching the videos, right? So in a sense, the students in the room are helping to make those videos more vibrant and watchable.
Yes.
But if they weren't here, it'd be kind of hard to keep the dynamic going.
Exactly, and without the audience, I think I cover 100 slides in an hour.
Yeah, cool. Okay, well, great.
Thank you all.